Hi, welcome everybody. Hopefully you found this okay. Due to the overwhelming disdain for UNLV's internet while we did our last chat, we are going to do a video for today rather than meet on Google Meet. So let me know how this works for you guys. Hopefully it's not an inconvenience. I'm recording this at a little bit earlier than our class, so hopefully I'll get it uploaded quickly enough and then get an email out to you letting you know how to get here. But let me know how you like this, if you like this better than trying to listen to me or watch me be all choppy through a Google meeting. But we're going to jump into it here. We left off in the middle of 1.6. And so we talked about 1.6 is inequalities, linear inequalities. And we talked about the addition principle of linear inequalities. So if I had something like, say, x plus 2 is greater than 4, I can use the addition principle, in this case by subtracting 2 from both sides. And this is given to me for free, right? I've solved it. X is greater than 2, right? Which is how you would read this. X is greater than 2, right? Oops, that's not helpful. I can't move this. Why can't I move this? There we go. So if I have something like, say, x plus 3 is less than whatever 10. Let's do not plus. Let's do minus. But it's the same thing. I can add 3 to both sides to isolate the x. In doing so, I have x is less than 13, and I've solved it. This is the inequality that describes all of the values that solve this, anything less than 13. Right? So if I want to write these in a set notation, this x is greater than 2 is any number from 2 to infinity, but not including 2. And also, since infinity is infinity, it's in a parentheses, it also gets that parenthesis. Right? Likewise, x is greater than 13 in interval notation is, or sorry, x is less than 13 in interval notation is all of the numbers between negative infinity and 13, not including 13, because of the strict inequality, right? Now, let's talk about the multiplication principle, right? When we talked about the addition principle, we said if you write something that's true, and as long as you add the same thing to both sides, right? If I add 8 to both sides, on the left-hand side, I get 10, 8 plus 5, 13. So my original inequality, 2 is less than 5 by 3. And if I add 8, there's still difference by 3. I'm never going to change that. As long as I add the same thing to both sides, I'm never going to change how much different the left side is from the right side. And that's why the addition principle is given to us for free. But, excuse me, if I do the same thing, let's say I've got 2 is less than 5, and I come in here and multiply both sides, let's say by 3, right? In my original inequality, there's a difference of 3, but after I multiply the left-hand side, 3 times 2 is 6. On the right-hand side, 5 times 3 is 15. I've changed how much different these are, and that might pose a problem to us. Right? The difference between 6 and 15 is now 9. Right? In fact, it's different by a factor of 3, not surprising. Right? It's still true, though. 6 is still less than 15, right? And so it seems like we're okay, right? But if I take that same inequality, 2 is less than 5, And if I multiply it, and it doesn't matter how big these numbers get, if I multiply it by 100, that inequality is still going to stand. It's still going to be a less than, because 2 times 100 is 200. 5 times 100 is 500. It's still, the left side is less than the right-hand side. So as long as I'm multiplying by whatever big positive number, I don't have any problems. I don't have any issues. Oops, that's not helpful. The issue comes when I take that same 2 is less than 5 and I multiply it by, let's say, a negative number. Let's say negative 10. Right? But 2 times negative 10 is negative 20. 5 times negative 10 is negative 50. But negative 50 is a smaller, it's a less number. It's a more negative number than negative 20. So I have to flip that inequality, right, in order to make this true. And we'll see that happen every time. So if A is less than B, and I take C to be some positive number, if C is greater than 0, then A times C is still less than B times C, as long as C is positive, right? But if C is negative, ooh, that's not helpful. Can I undo it? Undo. No, there it is, right. So again, as long as C is positive, then we're okay. Then the multiplication principle still follows. But if I have A is less than B, but C is less than 0, if it's a negative number, then A times C now becomes greater than B times C, right? So what I'm trying to say here is that if you multiply an inequality by a negative number, you have to flip that inequality. Greater thans become less thans will be greater thans, right? So, for example, if I have 3x minus 5 is less than 6 minus 2x, we're going to use those 2 principles just like we did in equalities and solve. I want to get maybe all of my x's to the left-hand side, so I'm going to add 2x to both sides. And I can do this all in one move. Since my x's are going to the left, I can also add 5 to both sides in the same step. That gets my 5 out of the left-hand side. 3x plus 2x is 5x. Still less than, because the addition principle was free, right? Then I have 6 plus 5, that's 11. And then I can divide by 5, right? And so this up here, the multiplication principle works whether you're multiplying or if you are dividing. It's the same thing, right? I'm dividing by a positive number, so I don't have to change anything. And so then I have isolated x on the left. It's still less than, and then it's 11 fifths. And if you need to pause this, I'm not going to wait because nobody's sitting here. But if you need to pause it, pause it. And let's look at this one. 13 minus 7x is greater than or equal to 10x minus 4. Right. Again, I'm going to move all of my x's to the left, right? So I'm going to subtract 10x from both sides to get them to the left. It's gone out of there. But since I'm moving my x's to the left, I'm also going to get my whole number out of the left and move it to the right by subtracting 13 to both sides. So now I've got negative 7x and negative 10x is negative 17x is greater than or equal to negative 17, conveniently enough. And when I divide, I'm going to divide by negative 17. Excuse me, sorry. And since I'm dividing by a negative, I have to be careful with that because the very first thing I do, if I'm dividing by a negative, then the very first thing I do is I'm going to flip that, and my greater than or equal to becomes a less than or equal to, and I've got x isolated on the left. Negative 17 divided by negative 17 is 1, right? So that means that my solution set is any number less than or equal to 1, and you can plug that back up into the original inequality and check it out. Grab a number like 0, -10, whatever, something less than 1. And so my interval notation for this would be everything up to and including 1. And so parentheses, -infinity, up to 1, bracket. All right. And then we have compound inequalities. So when we see compound means two inequalities joined by and or. And when you see and, it means that whatever the solution is, it has to satisfy both of those equalities, and you get the intersection. And then when you see or, it means it can satisfy one or the other or both. And so you're going to end up with a union on this guy. We notate an intersection typically by an upside down U and then the union with a U, or it's kind of a usually elongated U looking like that. This symbol, though, we're not going to use a whole lot because the intersection should just be one not disjoint set. And so it should just, you should never have to actually use this symbol in your solutions for this section or this class. But we will see this union symbol. We'll see that come up. So let's take a look and see what these look like. We might have, for example, -3 is less than 2x plus 5, or sorry, minus 5. Oh, just kidding, I'm looking at two different examples. Yeah, 2x plus 5. And we might have 2x plus 5, again, is less than or equal to 7. Okay. So there we have it. It's two inequalities just conjoined by the word and, right? And so we'll solve each one of these individually. We'll start with the one on the left. I'll start by subtracting 5 to both sides. I don't have to worry about changing the inequality symbol because it's the addition principle that I use there. And if I divide each side by 2, I've got one of my inequalities simplified down. And the other one, kind of same story, -5 from both sides. That leaves me with 2x is less than or equal to 2. And if I divide each side by 2, I have x is less than or equal to 1, right? And so I've got these two things. They're joined by an and. And I can rewrite this second one. If you don't like the x on the right-hand side, you can flip this all around. That's x is greater than -4, right? So if I look at what the solutions of these guys look like, x is greater than -4, looks like this on a number line, straightest number line ever. But let's just call this 0. Here's -4. And so it's anything greater than it. So it's that open circle and then shade it to the right. It's everything to the right. Now, when I go and graph the other guy, x is less than or equal to 1, I want my graphs to kind of line up. So I want 0 in the same spot. I want -4 in the same spot. Otherwise, it's going to be hard to see these where these overlap. But x is less than or equal to 1. Well, 1 is over here, right? So call 1 there if you need. But less than or equal to is an open, I'm sorry, a closed, a filled in circle, and then everything to the left, right? And then the intersection is, if I were to take those two lines and squish them down, where the overlap happens. So that's this bit here is shaded on both of those lines, right? The number 1 is shaded here. It's part of the shaded part, and it's shaded here, so it's included. But this -4 is not included in the black line, but it is included in the blue line. But it has to be on both lines to be in the intersection, so it's not in my final answer. And so when I'm putting the intersection of these two together, both of them together, 4 is excluded because it's not a solution to the black one. 1 is included because it's a solution to both, but all of the area to the right is not included. All of the area to the left is not included, so it's just between those two values. And so my final interval notation solution here, this is -4, this is 1. It's from -4 to 1. Not inclusive on the -4, but inclusive on the 1. And that's our and compound inequality. An or looks like where's my marker? 2x minus 5 is less than or equal to -7, or 2x minus 5 is greater than 1. So again, I'm going to solve both of these individually. So I'll add 5 to both sides here. That gives me 2x is less than or equal to -2. Divide each side, and I have this one down to x is less than or equal to -1. Or add 5 to both sides. And I've got 2x is greater than 6. Divide each side by 2, and I have x is greater than 3, right? So again, I'm going to graph both of these separately and then join them together. So if I graph x is less than or equal to -1, there's 0. Let's call this -1. To be less than or equal to -1 is a filled in or an closed circle at -1, and then everything to the left. For x is greater than 3, there's 0, there's -1. Here's 3. Let's throw 3 on both of them. But greater than 3 is an open circle at 3 and everything to the right. But when we say or, it means it could be a solution to one or both, or even one or the other, or possibly even both, right? So when we combine the solutions to these two, it's going to be anything that's highlighted anywhere, right? So these guys right here, they're highlighted, and so they're going to be part of my solution set because they're part of one of the solutions. So at -1, that's going to be filled in, and all of these guys are included. But we're inclusive here, so all of these guys over here, they're also part of it. But not -3, because -3 is not a solution on either of them. But it is everything to the right of 3. I think I said -3, I meant. And so it's that disjoint set here that I have. And this is where I'm going to write this as a union of two sets. This first one is -infinity to -1 with a bracket and a parenthesis around infinity. This other one is from 3 to infinity, parentheses on both sides, and then you just tap a union symbol between the two, and that is your final solution in interval form. All right, that's it. It was a pretty quick one today. That's all we didn't get through the last time. I do have I don't have it, so never mind. I'm just going crazy. But if you have questions, bring them to class tomorrow or send me emails or whatnot. Yeah, in class tomorrow might be a great time to ask any questions you have. So we'll call it for today. Hope you guys have a great rest of your day, and I will see you tomorrow.